So myself, I am Varad Dav, a doctoral student at the Department of Chemical Engineering, IIT Kanpur, right? And so in the last class, what we have seen? We have seen about the dual nature of matter. First of all, we have seen the limitations of Bohr models, and one of the limitations of Bohr's model was that it could not explain the dual particle and wave-like nature of atom, subatomic particles, and hence that was one of the major drawback of Bohr's model, and hence then we delved into this what is the dual particle nature, dual particle and wave-like nature. Then we studied some experimental results which supported the experimental, which suggested that atom is a particle. Atom shows particle-like behavior. While other also we have while we also saw about the experimental results such as interference and diffraction, which showed that it is a wave-like nature. So we studied about this dual particle wave-like nature, and then further we discussed about the de Broglie relationship, and we showed that there is a wavelength associated with every object in the universe, and the this wavelength, however, for massive objects like macroscopic level objects, this wavelength is less, and for subatomic particles this wavelength is huge, and hence at macroscopic level we see the particle nature is dominated because the wavelength is less, whereas at the subatomic or atomic level the wavelength characteristics dominate over the particle nature because of the wavelength, larger wavelength, right? So now so in today's class we are going to see about this de Broglie relationship in detail. Then further also we are going to study about the Heisenberg uncertainty principle. Then we are going to solve a couple of examples. And then at the end, if the time permits, we are going to delve into quantum mechanics. Slight introduction to quantum mechanics, right? Structure of atom, lecture 11, right? The first topic which we are going to study is derivation of Bohr's postulate, right? Of quantization of angular momentum from de Broglie relationship, right? So de Broglie equation help us in explaining the Bohr's postulate regarding the quantization of angular momentum of an electron, right? Now let us consider an electron moving around the nucleus in the form of wave in a circular orbit of radius r, right? So let me drag a picture. So let us consider that the electron is moving in a circular orbit. So let's say this is the circular orbit, right? Consider an electron moving around the nucleus in the form of wave, right? In a circular orbit of radius r, right? So let's say the radius is the r, right? The wave train of electrons may be continuous. So the wave nature could be in a continuous. So this is an electron wave with in phase, right? In phase electron wave, where this is out of phase electron wave, right? In phase, out of phase, right? And this figure represents the representation of electron waves and orbit in phase. So this is in phase and this is out of phase. If the two ends of the wave meet to give a regular series of crests and troughs, then the wave is said to be in phase, right? So this is a wave in phase. If the two ends do not meet to give a regular series of crests and troughs, it is said to be out of phase. So this is out of phase, right? As evident from this figure, right? From this figure, for wave motion to be continuously in phase, the circumference of circular orbital, right? So the circumference of the circular orbit must be an integral multiple of number of waves, right? Otherwise, the wave would interfere destructively and cannot and cancel each other and thus destroy itself, right? Therefore, by considering the electron as wave, we automatically impose a limit to the number of orbits, right? Let us write this down from figures present in next slides, right? We conclude that for by considering electron as wave, we automatically impose a limit to the number of orbitals, number of orbits, sorry, right? It is clear that the circumference of the orbit, right? Circumference of the orbit must be integral multiple of the electron wavelength, right? Right? So in other words, mathematically we can define that 2 pi r should be n lambda, right? This is the circumference and this is the integral multiple of electron wavelength, right? Lambda is equals to electron wavelength. From de Broglie relationship, what we have? We have lambda is equals to h by mv, right? Where h is the Planck's constant, m is the mass of electron, right? What does this mean? Right? So we substitute what we get 2 pi r is equals to nh by mv, right? That means mvr is equals to nh by 2 pi, right? Sometimes this h by 2 pi is also called as h cross, right? So mvr is nothing but n into h cross, where h cross is h by 2 pi, right? What can we draw from this expression is the angular moment of an electron should be an integral multiple of h by 2 pi, right? In other words, the angular momentum is quantized. This is the same as Bohr's condition for quantization of angular momentum, right? So what does we conclude from here? We conclude that thus the angular momentum of the electron should be an integral multiple of h by 2 pi, right? What does this mean? In other words, the angular momentum is quantized. This is same as the Bohr's condition of quantization of angular momentum of fixed energy orbits. Now let us discuss about the number of waves in nth orbit. By definition, we know that this is going to be equal to circumference of the nth orbit divided by the wavelength, right? It is nothing but 2 pi r by lambda, but we know that this must be an integral multiple of, right? So first we use de Broglie's wavelength, lambda is equals to nh by 2 pi, right? So we substitute it here, nh by 2 pi, which comes out to be r by, right, h by mv. Sorry, this is h by mv, right? Is h by mv, which is nothing but what? 2 pi into mvr by h, right? But we know that mvr is nothing but mvr is equals to nh by 2 pi, right? Just now we saw, right? mvr is equal to nh by 2 pi, right? Hence, when we substitute, what we get is 2 pi nh by 2 pi divided by h, which is nothing but n. Hence, number of waves in nth orbit are nothing but the n value, right? This is very important, right? So now let us discuss about distinction between electromagnetic waves and matter waves, right? Distinction between electromagnetic waves and matter waves. So here we are going to write electromagnetic waves, matter waves. The first point is electromagnetic waves are associated with electric and magnetic fields perpendicular to each other and to the direction of propagation of radiation, right? Whereas matter waves may not be associated with electric and magnetic fields. So electromagnetic waves are associated with electric and magnetic field perpendicular to each other and to the direction of propagation of radiation, right? Whereas matter waves may or may not be associated with this. Matter waves may not be associated with electric and magnetic field. The second point is that electromagnetic waves can be radiated into space or emitted, right? Matter waves are neither radiated into the space nor emitted by the particles, right? These are simply associated with the particles, right? So electromagnetic waves can be radiated into space or emitted. Matter waves are neither radiated into the space emitted by the particles, right? They are simply associated with the waves. They are simply associated with the particles. Electromagnetic radiations or waves versus matter waves. Our point is going to be electromagnetic waves do not require any medium for propagation. That is, these waves can pass through vacuum, whereas matter waves require medium for propagation. That is, these waves cannot pass through vacuum. Do not require any medium for propagation, whereas these require medium for propagation. Fourth point is all electromagnetic waves travel with the same velocity, whereas matter wave travels with different velocities. All electromagnetic waves travel with same velocity, okay? Matter waves travel with different velocities. Right? The velocity of all the electromagnetic waves is right with the same velocity, and the speed is that velocity is nothing but speed of light meter per second. Right? The wavelengths of electromagnetic radiations are much larger and are given by normal radiation, that lambda is equal to c by v, whereas for matter waves we have de Broglie relationship, right? So the wavelengths of electromagnetic radiation are much large and are given by the relation lambda is equal to c by mu, right? So mu is the frequency, right? Whereas matter waves have shorter wavelengths given by de Broglie relationship, right? H by m, right? Now we are going to study about the Heisenberg's uncertainty principle, right? So far we have been believing that anything can be specified to any desired degree of accuracy, right? However, Heisenberg in 1927 put forth the principle known as Heisenberg's uncertainty principle, right? So the definition of this Heisenberg uncertainty principle is: it is not possible to measure simultaneously both the position and momenta of a microscopic particle with an absolute accuracy, right? So this is the statement of Heisenberg uncertainty principle, which state it is not possible to measure simultaneously both the position and momenta are called as velocity of a microscopic particle right, with absolute accuracy, right? Right? So mathematically we can say maybe expressed as delta x, select for this, delta x multiplied by delta p greater than equal to h by 4 pi, right? Where delta x is nothing but uncertainty in position, whereas delta p is nothing but uncertainty in momentum, right? The sign greater than or equal to here means that the product of delta x, right? So the product, so this sign means that the product of delta x and delta p, it can never be less than h by 2 pi, right? That means even in best case it cannot be zero, right? It always has to be greater than some particular value, right? And the consistency of the product of uncertainties means that if delta x is small, right, then the position of the particle is measured accurately, then delta p would be large, right? That is, there would be large uncertainty in its momentum. On the other hand, if delta p is small, the momentum of the particle is measured more accurately, whereas delta x would be more, right? That would be a larger uncertainty with regard to the position of particles, right? In other words, if the position of particle is measured accurately, there will be more error in the measurement of momentum, and conversely, if momentum is measured more accurately, the position will not be accurately known, right? So let us write it in here. So what we get from here is, in other words, if the position of a particle is measured accurately, right, then there will be more error in the measurement of momentum, right, and vice versa, right? So because delta p is nothing but m into delta v, we can also say that delta x into m delta v is nothing but has to be greater than or equal to h by 2 pi, right? And when we take this m to the other side, this means that delta x into delta v greater than equal to uncertainty principle. So this is in the form of momentum, right? Because delta p is here, and obviously we don't have any uncertainty in the measurement of mass, right? So when we write delta p as m into delta v, we just take the m to this side, and we have uncertainty in the position multiplied by uncertainty in the velocity has to be greater than or equal to some positive volume which is h by 2 pi m, right? So this also means that the position and velocity of an object cannot be simultaneously known with accuracy. This is true only for the subatomic particles, right? This also means that the position and velocity of an object cannot be simultaneously known with accuracy, right? So now let us try to understand the physical concept, right? The physical concept of uncertainty principle. Physically, what does this mean? Uncertainty principle. Now, in order to understand this, let us take a. So, in order to understand the physical concept of uncertainty principle, let us study as to how the position of a material object is determined, right? To determine the position of an object, we must be able to see the object, right? This can be done with the help of light of suitable wavelength, right? When the beam of light falls on the object, right? This is here, this is the object, and this is the incident photon. When it falls on the object, right? And the reflected ray enters our eye, we get to know about the position of the we get to know about that part of the about that object, right? Now if the object is large, its position and velocity will not change by the impact of striking photons, right? Thus it will be possible to determine both the position and velocity of the object simultaneously. However, in the case of microscopic objects such as electron, the interaction of striking photon of light with particle will cause appreciable displacement of the particle from its normal path, right? So this was the original. So this was the original path of electron. Had the incident photon not been hit by it, it would have continued to go in this path. It would have continued to go in this path, right? Because the incident photon interacted with this electron, and because of the collision between this incident photon and electron, the electron changes position from this path to this path. Why? Because the interaction between those two things is of comparable nature. Had this been a microscopic object, in that case, the incident photon collision of these two things would not have caused so much of difference, right? But because of subatomic particle, this uncertainty remains, right? However, in case of microscopic objects such as electron, the interaction of striking photon of light of the particle, right? The interaction of striking photon of light with the particle will cause appreciable displacement of the particle from its normal path, right? Hence, as a result of this, the particle undergoes a considerable change in its path and velocity due to the impact of single photon used to observe it. Thus, the very act of measuring the position of microscopic particle causes a change in its momentum, right? So this figure, right? So this figure shows us the how the position of an electron changes by the impact of photon, right? The collision of photon with the electron sends in an unprecedented direction, right? Thus, it is not possible to determine simultaneously the exact position and momentum of the electron or any other microscopic object, right? Now, let us understand the significance of uncertainty principle in our daily life. So one of the important application of the Heisenberg's uncertainty principle is that it rules out the well-defined circular orbits, right, or trajectories proposed by Bose. Uncertainty principle rules out the well-defined circular paths or orbits proposed by Bose. Right? Since the subatomic particle, like an electron, it is not possible to simultaneously determine the position and velocity at any moment with good degree of precision, right? Therefore, it is not possible to talk about the trajectory of an electron or well-defined circular orbits. It should be borne in mind that the uncertainty principle is not due to the lack of sufficiently refined techniques, but it is due to the fact that we cannot observe microscopic things without disturbing them. No microscopic things, right? No instrument can observe the position of an electron without affecting its motion. In other words, uncertainty principle is the fundamental limitation of nature, right? So, uncertainty principle is the fundamental limitation of nature, right? Thus, we cannot design an experiment to obtain an accurate value of both position and momentum of microscopic object. However, in our daily life, this principle has no significance, right? This is because we come across only large objects, right? That is the objects which we can observe with naked eye without altering their position, right? Without altering their motion. The position and velocity of these objects can be determined accurately because in these cases, during the interaction between the objects and the measuring device, the changes in position and velocity are negligible, right? Okay. Now we are going to solve couple of sample examples, right? So first question is a tennis ball of mass 6.0 10 raised to power minus 2 kg is moving 62 meter per second, right? Calculate the wavelength associated with this moving tennis ball. Second question is, will the movement of this ball exhibit a wave character? Right? Basically, what we are asked to find, we are asked to find the de Broglie wavelength. Right? So, according to de Broglie, we know this is nothing but h by mv for problem at hand. So, this is the Planck's constant, right? And we know the mass of the particle is tennis ball is 10 raised 6 into 10 raised to power minus 2 kg and velocity is 62 meter per second. Lambda comes out to be around 1.8 10 raised to power minus 34 meter, right? So clearly this is very less, right? This wavelength is too small to be measured and thus therefore the wave nature of ball cannot be detected. Wave nature of ball cannot be detected, right? Thus the ball will not have wave-like character, right? Let's move on to the next question. Question number 2. A golf ball has a mass of 40 kilograms and a speed of 45 meter per second. Right? If the speed can be measured with an accuracy of 2%, calculate the uncertainty in position. So here we are going to use uncertainty principle, right? So we are given uncertainty in the velocity is nothing but 45 meter per second, right? Which is nothing but sorry, this is the velocity, right? Sorry, this is the velocity, right? And uncertainty has been given by what? Uncertainty is given by 2%, right? That means uncertainty is nothing but 0.02 multiplied by this 45, which comes out to be 0.9 meter per second, right? And we know Heisenberg's uncertainty principle. According to that, delta x into delta v greater than equal to h by 4 pi m, right? This means delta x has to be greater than equal to h by 4 pi m into delta v. That means delta x has to be greater than equal to 6.626 10 raised to the power minus 34 divided by 4, 3.14 into m, right, which is 40 kg, 40 into 10 raised to the power minus 3 kg, right, multiplied by 0.9. Hence delta x comes out to be around greater than or equal to 1.46 10 raised to the power minus 33 meters, right. This is the uncertainty in its position, right. So now we are going to talk about the short introduction to quantum mechanics, right. So quantum mechanical model of atom and concept of atomic orbital. So the wave character of an electron and the uncertainty in its position and momentum gave a serious blow to the Bohr's model of an atom, right. So according to Bohr, the electrons revolve around the nucleus in certain well-defined circular orbits, right. But the idea of uncertainty in position and the velocity overruled Bohr's picture of fixed orbits. Thus, the classical mechanics could not describe the behavior of electron in atom correctly. Therefore, the scientists started looking for a model which could incorporate the dual nature of matter and the uncertainty principle, right? And this resulted in a new approach called as quantum mechanics or wave mechanics, right? To overcome Bohr's model limitation, a new approach called quantum mechanics or wave mechanics was created, right? This is a branch of science that takes into account the dual behavior of matter. The quantum mechanics is a theoretical science which deals with the study of motion of the microscopic objects like electrons, which have both observable wavelength particle and properties. Okay. So, quantum mechanics is a theoretical science which deals with which deals with the study of the motion of microscopic objects like electrons, which have both observable wavelength and particle-like properties. Quantum mechanics was developed independently in 1926 by Werner Heisenberg and Erwin Schrödinger. On the basis of quantum mechanics, Schrödinger proposed a model of an atom which considered wave-particle duality of matter and Heisenberg's uncertainty principle. This model was known as quantum mechanical model of atom. Right? In 1927, Erwin Schrödinger described the wave motion of an electron in three-dimensional space around the nucleus by a mathematical equation known as Schrödinger's wave equation. Right? And the Schrödinger wave equation is given by this expression: del 2 psi by del x square plus del 2 psi by del y square plus del 2 psi by del z square plus 8 pi square m by h square into e minus v of psi, sorry. This is Schrödinger's wave equation, right? Where psi is the amplitude of the wave, x, y, z are the coordinates of position of electron, coordinates of position of electrons, and A is the total energy of electrons. V is the potential energy, right? So V is the potential energy. M is the mass of electron, and H is the Planck's constant. Mass of electron and H is nothing but Planck's constant. This simple equation, right? This complex expression can also be written in a simplified manner as following, which is H psi is equal to E psi, right? H psi is equal to E psi, where H is the Hamiltonian operator, and the solutions of Schrodinger equation wave gives E and psi. The solution of Schrodinger wave equation give E and psi. Although the Schrodinger wave equation was difficult to accept at first, it has now gained wide acceptance, right? This is because the result obtained from Schrodinger wave equation are in excellent agreement with the experimental findings. One of the major achievements of Schrodinger wave equation are that it successfully incorporates the experimental information about atoms and molecules. So this is where we end our today's class, right? So in today's class, what we have seen is uh, we have seen about the Heisenberg's uncertainty principle, right? And then we have seen that why the Heisenberg's uncertainty principle exists and why it is dominating at macroscopic scale, right? Then we have also seen the significance of uncertainty principle in our daily lives. Further, we have solved some couple of examples, right? And at the end, we have a little bit touched upon the quantum mechanical model of an atom and atomic orbitals, right? So so I thank you all for attending this class, and I hope to see you again in the next class. Thank you. Hello everyone. I welcome you all to this 12th lecture of Structure of Atom. Myself Bharat Dow. I am a doctoral student at the Department of Chemical Engineering, IIT Kanpur. So in the last class, what we have seen about the Heisenberg's uncertainty principle, which tells us about that. First, we studied about de Broglie wavelength, and then we studied the Heisenberg uncertainty principle. So de Broglie wavelength states that each particle has a wavelength characteristic wavelength associated with it, and the wave behavior of matter becomes dominant at the subatomic level, whereas at the microscopic level, the particle nature of matter becomes dominant over its wave nature. Right. Then further we studied about the Heisenberg's uncertainty principle. So Heisenberg's uncertainty principle states that it is not possible to measure simultaneously both the position and momenta of a microscopic particle with an absolute accuracy, right? So we can, if we measure accurately the position, there will be uncertainty in its momentum and vice versa. And both the things cannot be measured with 100% accuracy, right? And then we also studied about Heisenberg's uncertainty principles, a practical application. Then at the end of the last class, we delved into the quantum mechanics and studied about the quantum mechanical model. We also studied about the Schrodinger's wave equation, right? So let me first try. So we studied about the Schrodinger wave equation, which was del 2 psi by del x square plus del 2 psi by del y square plus del 2 psi by del z square plus 8 pi square ms square into e minus v phi is equal to 0, where phi was called the phi was the amplitude of the wave, x, y, z are the coordinates of the position of electron, E is the total energy of the electron, V is the potential energy, and M is the mass of the electron, right? And H is the Planck's constant, right? We also studied that this expression could also be written in the form of H psi is equal to E psi, right? Where this stands for the Hamiltonian, that is the operator, right? Hamiltonian operator, right? And we also studied about the significance of Schrodinger wave equation, right? So today we are going to build upon on that. This is lecture 12, structure of atom, right? So first, what we are going to study, about the operators. H psi is equal to E psi was there, right? Where this H stands for the Hamiltonian operator, right? So while studying the state of a system, we make various measurements of its position, of its properties, such as mass, volume, momentum, position, and energy. Each individual property is called as observable, right? in order to determine the value of observable property, we have to perform certain mathematical operations, and this operation is represented by an operator, right? Therefore, operator is a mathematical command or instrument or instruction which acts as a mathematical function, right? So, an operator is a mathematical command or instruction which acts on a mathematical function. Okay? Like for example, in the equation 4 into 5 is equals to 20. The operator is multiplication, right? The operator is multiplication, right? And the operator is x. The operator is x, right? So we can also express the multiplication operation with some symbol, right? So express the multiplication operation. Multiplication operation as an with some symbols, right? Let's say we designate as m cap, right? So for example, then this 4 into 5 will turn to what? Equal to 20. This operation will turn as m cap of 4 into 5 is equal to 20, right? So in this case, m cap is the multiplication operator, right? Where the cap, this is the cap, signifies operator. So with this understanding, we'll go to the Schrodinger wave equation for hydrogen atom. Schrodinger wave equation for hydrogen atom, right? So the first point of this is when Schrodinger wave equation was solved for hydrogen atom, the solution gives the possible energy states or energy levels that an electron can occupy. These values of energy are called as eigenvalues, and the corresponding values of wave functions, that is psi of the electron associated with these energy values, are called as eigenfunctions, right? So let us write this down. When Schrodinger wave equation was solved for hydrogen atom, right? The solution gives the possible energy states or energy levels that an electron can occupy, right? And these values are called as eigenvalues, right? The corresponding values of the wave function on the other end. The corresponding values of wave function on the other end are called as eigenfunctions, right? The second point of this is the wave functions and the corresponding energy states are characterized by a set of three quantum numbers called as principal quantum number, azimuthal quantum number, and magnetic quantum number. So we are going to study about all these quantum numbers in our subsequent classes. These numbers arise as a natural consequence in the solution of Schrodinger wave equation. This quantum mechanical model of hydrogen atom successfully predicts all aspects of hydrogen atom, all aspects of hydrogen atom spectrum and other phenomena which could not be explained by Bohr model, right? So what we are saying is let us write this down. The wave function and the corresponding energy states. The wave function and corresponding energy states are characterized by a set of three quantum numbers. Set of three quantum numbers. These quantum numbers are called as principal quantum number, which is denoted by the symbol n. Right? Azimuthal quantum number. Azimuthal quantum number, which is denoted by the symbol L, and magnetic quantum number, which is Ml, right? These numbers arise as a natural consequence in the solution of Schrodinger wave equation, right? And this quantum mechanical model of the hydrogen atom successfully predicts all aspects of hydrogen atom spectrum, right? And other phenomena which could not be explained by Bohr model, right? Bohr's model, right? So the third point of this expression is Schrodinger wave equation is the Schrodinger wave equation cannot be solved exactly for multi-electron system, right? However, approximate methods can be used to get the solution of reasonable accuracy, right? So this is the advantages of Schrodinger wave equation. So the third point, let us write down. Schrodinger wave equation cannot be solved exactly for multi-electron atoms. However, approximate methods can be used to get the solution. So let us understand the next topic which we are going to cover is physical significance of wave function, which is denoted as psi, right? So in physical sense, psi gives the amplitude of the wave associated with the electron, right? So we know that in case of light wave, the square of the amplitude of the wave at a point is proportional to the intensity of light, right? So what is basically psi basically gives the of the wave with electron, right? And the square of the amplitude of wave at that point, right, is proportional to the intensity of light, and the square of amplitude is proportional to the intensity of light, right? Extending the same concept to the electron wave motion, the square of the wavelength may be taken as intensity of electron at any point, right? Intensity of electron. In other words, psi square determines the probability of finding the moving electron in a particular region, right? That means it gives the probable density. Thus, psi square has been called the probability density and psi as probability amplitude, right? Okay, that means psi square determines the probability of finding the moving electron in a given region, right? That is, it gives the probability density, right? Hence, what we can say is, hence, psi square has been called the probability density, psi as the probability amplitude, right? Hence, the solution of Schrodinger wave equation replaced the discrete energy levels or orbits proposed by Bohr and led to the concept of most probable regions in space in terms of psi square, right? This is also important. We should write this down. Hence, the solution of Schrodinger wave equation replace the discrete energy levels or orbits proposed by Bohr and led to the concept of most probable region in spacetime. Most probable region in terms of psi square, right? A large value of psi square means that a high probability of finding the electron at that place, and a small value of psi square means that low probability, right? Higher the psi square, very high, a psi square high means probability of finding an electron is high. If psi square low, then that means that probability of finding an electron is low, right? Therefore, the wave mechanics approach gives meaningful wave functions which describe the position and energy levels of an electron in atom, right? Therefore, the wave mechanics approach gives meaningful wave functions describe the position and energy levels of electrons in an atom, right? Now let us move on to the next topic, which is important features of quantum mechanical model of an atom, right? So important features of the quantum mechanical model of atom. Right? The important features of quantum mechanical model are summarized. Right. So first is the energy of electron in atom is quantized. That is, they can have only certain specific values. Right. Which was also the Bohr's model. Right. This was also proposed by Bohr's model. The energy of electron in atoms is quantized. That is, they can have only certain specific values. Right. Second is the existence of quantized electronic energy levels in a discrete discrete results of wave like properties of electron and are allowed the solutions of Schrodinger equation. Right. So the existence of quantized electronic energy levels is a direct result of the wave-like properties of electrons are the allowed solution of Schrodinger equation. Right. Third point is this gives the most probable region in an atom where the probability of finding the electrons is maximum. Therefore, this model is in accordance with the Heisenberg uncertainty principle and does not specify the exact position and moment of the electron, but it talks about the most probable region called as orbitals. Right? This gives the most probable region in an atom. Right? Where the probability of finding the electrons is maximum. Right? Therefore, this model is in accordance with the Heisenberg uncertainty principle. Right? And does not specify the exact position and momentum of the electron. Right? But it talks about most probable regions called as orbitals. Right? The fourth point is an atomic orbital is described with the help of wave function for an electron in an atom. Whenever an electron is described by wave function, we say that the electron occupies that orbital. Right? Since many wave functions are possible for an electron, there are many atomic orbitals in an atom. In each orbital, an electron has definite energy. Thus, all the information about the electron in an atom is provided by its orbital wave function. Right? An atomic orbital is described with the help of wave function, which is psi. Right? For an electron in an atom, right? Right? Whenever the electron is described by wave function, right? Whenever an electron is described by wave function, we say that the electron occupies that. We say that the electron occupies that orbital, right? There's many wave functions are possible, right? Since many wave functions are possible, right? Are possible for an electron. There are many atomic orbitals in an atom. In each orbital, an electron has definite energy, right? In each orbital, an electron has definite energy, right? Thus, all the information about the electron in an atom is provided by its orbital wave function, right? Which is nothing but psi, right? The fifth point is the probability of finding the electron at a point within an atom is proportional to the square of the wave function, right? At that point. Therefore, psi square is also known as probability density and is always positive, right? The fifth point is the probability of finding the electron at a point within an atom is proportional to the square of the wave function. Square of the wave function. Just nothing but psi, mod of psi square, right? At that point, right? Therefore, psi square is also known as probability density and is always positive. The probability of finding the electron in so 6 point is the probability of finding the electron in a region having a volume dV can be obtained as psi square into dV, where dV is the infinitesimally small volume, right? The probability of finding the electron in a region having a volume dV can be obtained as psi square into dV, right? Where dV is the infinitesimally small volume which is Tx dy Tz, right? The 7 point is the quantum mechanical model gave three constants known as quantum numbers, which are required to specify the position and energy of an electron in an atom, right? And these we are going to study in the next classes, right? The quantum mechanical model K3 constant known as quantum numbers, right, which are required to specify the position and energy of the electron, position and energy of the electron in an atom, right? So now what we are going to study, next topic is so we are going to study about orbitals, orbit and orbital, right? The wave characteristics of an atom, of an electron, and uncertainty in its position gave a serious blow to Bohr's model. According to Bohr, the electrons revolve in a well-defined circular orbit, but the idea of uncertainty in position and velocity overruled the Bohr picture of fixed circular orbits. Scientists started looking for a theory which may explain the stability of an atom, the dual character of the atom, and uncertainty principle. So this resulted in a new approach called as wave mechanics in 1927, when Schrodinger described the behavior of electron by a mathematical equation known as Schrodinger wave equation. The solution of wave equation led to the concept of most probable region in a place of well-defined circular path proposed by Bohr. So according to this approach, we cannot simply say that the electron exists at a particular point, but we talk about the certain regions in space around the nucleus where the probability of finding the electron is maximum, and these most probable region are called as orbitals, right? And thus an orbital may be defined as a region in a space around the nucleus where the probability of finding the electron is maximum, right? So let's write this down. So orbital is the region in space, where around the nucleus where probability of finding an electron is maximum, right? If a boundary is drawn, so let us so if a boundary is drawn which encloses a region where there is high probability of finding the electron, right? The figures obtained gives the general picture of an orbital, right? So let us just picture. Let me drag a picture which represented. So this is a figure, right? So this is a figure, right? So this is the orbital, right? So the color indicates the probability of density. So darker color indicates high probability, and lighter color indicates the less probability. So you can see here this region is a darker one. That means there is a high probability of finding an electron. And as we move away from the center, the probability of finding an electron decreases. And this whole region is called as orbital, whereas only the boundary, right? This will be called as an orbit, right? So electron cloud representation of an orbital. So this is an electron cloud representation of an orbital, where this is an orbit, right? So orbital here is shown by dotted figure representing the electron cloud. The intensity of dot gives the relative probability of finding the electron in that particular region. It may be noted that there are some chances of finding the electron even outside the figure, right? Even outside. However, those are very small, right? So now let us write down the difference between orbit and orbital, right? The next topic is difference between orbit and orbital, right? So just write this down. So this portion we are going to write about orbit, and this portion orbital. This is like this. Okay. The first point is orbit is a well-defined circular path around the nucleus in which an electron revolves, whereas orbital represents the region in a space around the nucleus in which the probability of finding the electron is maximum. Right? Orbit is a well-defined circular path around the nucleus in which an electron revolves, right? Whereas orbital represents the region in space around the nucleus in which the probability of finding the electron is maximum. Second point is it represents the orbit represents the planar motion of an electron, whereas orbital represents the three-dimensional motion of an electron around the nucleus, right? So it represents the planar motion of an electron, whereas this represents the three-dimensional motion of an electron around the nucleus. The third point is orbit gives a definite path of an electron, and this concept is not in accordance with the uncertainty principle, whereas orbital does not specify defined paths, and according to this concept, electron may be anywhere in this region, and this concept is in accordance with the uncertainty principle. Orbit gives a definite path of an electron, and this concept is not in accordance with the uncertainty principle, whereas orbitals does not specify definite path. According to this concept, electrons may be anywhere in this region, right? And this concept is in accordance with the uncertainty principle. So move on to the next point. That is point number 4. So all orbits are circular, whereas orbitals have different shapes, right? For example, S orbital is spherical, whereas P orbital is dumbbell shape, right? So all orbits are circular, whereas orbitals have different shape. The fifth point is orbits do not have a directional constraint or characteristics, whereas except for S orbital, all other orbitals have directional characteristics. Okay? Orbits do not have directional characteristics, right? Whereas except S orbital, all other orbitals have directional characteristics. The last point is an orbit can accommodate electrons equal to 2n square, where n represents the principal quantum number, whereas an orbital cannot accommodate more than 2 electrons, right? An orbit, so this we are going to study, can accommodate electrons equal to 2n square, where n represents the principal quantum number, and orbital cannot accommodate more than 2 electrons, right? So these are the differences between an orbit and an orbital, right? So in the next class, so I'll give you a brief introduction. So quantum numbers. So in the next, the next topic is going to be quantum numbers, right? So there are 3 quantum numbers. So these are principal quantum number called as n, right? Then azimuthal quantum number, which is called as L, and the last one is the magnetic quantum number, right? The last one is going to be magnetic quantum number called as ML. quantum number which is called Mn. So the principal quantum number, so this quantum number determines the main energy shell or the level in which electron is present, and it is denoted by n. It can have whole number values starting from 1, such as n equal to 1, 2, 3, 4, and this quantum number also identifies as shell. The shells with n equal to 1 is called as first shell, right? And then n is equal to 2 are called as second shell, and so on and so forth. The principal quantum number also helps in determining the average distance of an electron from the nucleus, right? That is, if n is equal to 1, that is the first shell, it is closest to the nucleus and has the lowest energy. As the value of n increases, the distance of the electron from the nucleus increases, and also the energy of an electron in that shell increases, right? Thus, principal quantum number gives the average distance of the electron from the nucleus, right? Of and energy associated with it, right? So this is the what a new principal quantum number is, and azimuthal quantum number is basically orbital angular momentum is associated with orbital angular momentum, and it is denoted by L. So this is what we are going to study in the next class, and also we are going to study the magnetic quantum number. So in present class, what we have seen about the Schrodinger wave equation. We have seen what is called an operator and an example of operator. Further, we have seen the characteristics or the advantages of quantum mechanical model of an atom over Bohr atom. And then we have seen about the orbital, which is a concept of only this quantum mechanical model, and orbital basically gives the probability of finding an electron and is different from the orbit, okay, which was given by Bohr. So we studied about their similarities and differences, and also we in short studied about the different quantum numbers, right? So in the next class, we are going to study about these quantum numbers, and we are going to delve deeper into it. And further, we are also going to study about the quantum numbers associated with spins, and then we are going to study about Pauli's exclusion principle and Hund's maximum rule of multiplicity, right? That is what we are going to study in the next classes, right? But thank you all for attending this class, and I hope to see you again in the next class. Thank you. Hello everyone. I welcome you all to this 14th lecture of structure of atom. So myself, Bharat Dow, I am a doctoral student at the Department of Chemical Engineering, IIT Kanpur. Okay. In the previous class, we have seen about different quantum numbers, right? Principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. We have also studied about their symbolic representation, and we have also studied about in detail about what each quantum number stands for, and how with the help of these four quantum numbers we can uniquely determine or describe the electron, right? And we have also seen the maximum and minimum values of this quantum numbers, right? So in today's class, what we are going to see is we are going to see about the shapes of these orbitals, right? In the previous class, we have discussed about difference between orbits and orbitals, right? And then we studied about quantum numbers, and in today's class, we are going to study about how these electrons are distributed in these orbitals and orbits. So we are going to study some principles, right? So first, what we are going to study? First, we are going to study about the shapes of the orbital, right? The first topic is going to be the shapes of atomic orbitals, right? Shapes of atomic orbitals, right? So it has been learned that the probability of finding the electron does not become zero even at large distances from the nucleus. Therefore, it is not possible to draw any sort of geometrical figure that will enclose a region of 100% probability. However, for the sake of pictorial clarity, we draw figures in which the probability of finding the electron is maximum. And these most probable regions are called as boundary surface diagrams or orbitals, right? The first point which we are going to write is that we learned that the probability finding the electron does not become zero even at large distances from the nucleus, right? Hence, what we do is we draw figures in which hence we draw figures in which the probability of finding the electron is maximum. Right? It is about 90 to 95%. Right? And these most probable regions are called as boundary surface diagrams or orbitals. Right? Orbitals. Right? So we are going to the first topic. In this, we are going to study about radial wave function. Right? So the shape of our orbitals are determined from the variation of wave function, that is psi, as a function of r. Right? Shape of orbital is determined with the help of psi and r plots. Right? These are called as radial dependence or radial wave function. And these plots are called as radial wave functions. Right? The right. So these graphs are like this. An example of these graphs could be like this. Where right? Where this is psi. Right? This is the shape of 1s orbital where L is the 1, L value is 0. This is psi. This is R. Right? Let us call it as figure A, figure B, figure C. Right? This is psi versus R. Right? This is 2s orbital. N is equal to 2, L is equal to 0. Right? This is 2p orbital. N is equals to 2, L is equals to 1. Right? These are plots of wave function with distance from the nucleus. Right? So this graph shows the 1s, 2s, and 2p orbitals. Right? It is clear from this figure. This way that the wave function for 1s orbital continuously decreases with increasing r, where however for 2s orbital the wave function increases in the beginning with increasing r and then becomes zero at a particular distance, and this is what is called as node. Right? The wave function decreases in the beginning with increasing r, becomes zero at a particular distance, and then becomes negative. And the wave function for 2p orbital first increases to maximum and then decreases. Right? So it is very interesting to know that 2s wave function can be positive or negative. Right? Here it is positive, here is it negative. Depending upon the distance, it may be noted that the positive and negative signs refer to the signs of the wave function and have no connection to the positive and negative charges. Right? So this point has to be written down. Right? It has to be noted. Figure B, that the positive and negative sign I of r refer to the sign of wave function, sign of the wave function, and have no connection to the positive and negative charges. As we have seen for this 2s orbital, right? As we have seen for this 2s orbital, at a point the wave function becomes zero. Right? Here the wave function becomes zero. Right? Here the wave function tends to zero. The point at which the radial wave function becomes zero is called as radial node surface or simply a node. Right? This point also has to be written. The point at which radial wave function becomes zero is called, right? At the node, the value of the wave function changes from positive to negative. In general, it has been found that ns orbital have n minus 1 nodes. Similarly, np orbitals have n minus 2 nodes, and so on. The value of wave function changes from positive negative. So in general, ns orbital has n-1 nodes. Similarly, np orbitals have n-2 nodes, right? Where n is the value of the orbital, right? In all cases, psi approaches 0 as r approaches infinity, right? As r approaches infinity. Right? It may be noted that psi, that like psi, the plots of psi also do not have physical meaning, right? However, the importance of this plot lies in the fact that they give information about how radial wave function changes with distance and about the presence of node where the sign of psi changes. And this is particular importance in understanding the chemical bonding, right? So part B is going to be probability density graphs. What is probability density? It is nothing but psi square. Right? So according to German physics, Max Born, the square of the wave function gives the probability density of finding the electron at particular point. Probability density of finding the electron at a distance of r from the nucleus. The psi square plot for the figures which we have seen, right, in the previous class. In this, so this is the psi value, right? So this is the psi versus r. Now we are going to plot the same for psi square versus r, right? Psi versus r, and we are now going to plot the similar for psi square r. This is going to be like this. This is psi square versus r. This is going to be like this. This is psi square. This is figure A, figure B, figure C. This is r, right? This is psi square, right? And this is going to be the node. This is the plot of 1s orbital, 2s orbital, and this is 2p orbital, right? So these are the variations of psi square as a function of r, right? Obtained by plotting psi square versus r. The plots are for this 1s, 2s, and 2p orbital, right? These diagrams look similar to these diagrams, right? To this diagram, except that the because the square has been implemented, the negative side of this plots has been gone to upper side, right? These graphs are called as probability density graphs. It may be noted that for s orbital, the maximum electron density is at the nucleus, and for p orbital, it has zero electron density at the nucleus. It may be noted that all orbitals except s orbitals have zero electron density at the nucleus, right? So these graphs are called as, may be noted that for s orbitals, maximum electron density is at the nucleus, and for p orbitals, it has zero electron density at the nucleus. Right? It may be noted that all orbitals except s orbitals have zero electron density at the nucleus. right? So the next topic which we are going to study is radial probability function, which is nothing but 4 pi r square psi square, right? So psi square versus r plots gives the probability density for the electron around the nucleus. However, in order to determine the total probability of an infinitesimally small distance, we have to multiply the probability density by volume of the region, right? So in that case, is going to be probability is going to be right, which is nothing but psi square into dV. That is the volume of the differential region. Is the volume of differential region. Right? Since the atoms have a spherical symmetry, it is more useful to discuss the probability of finding electron in a spherical shell between the distance of r plus dr and r. To understand this, right? So let us try to understand this. Right? So what we have is, so what is the value of this dV? That is what we are going to find out. Right? So let us consider these are the values. So its radius is going to be r, and this is going to be r plus dr. Such that this distance is dr. Right? So volume of the shell, right? So volume of this shell, that is going to be what? Right? This is going to be 4 by 3 pi r plus dr cube minus 4 by 3 pi r cube, which is nothing but 4 by 3 pi. We are going to take constant r plus dr cube minus r cube 4 by 3 pi r cube plus dr cube plus minus 3 pi r dr. Sorry, it's going to be right. This is going to be 3 r dr multiplied by, or in other words, we can write this as plus 3 r square dr plus 3 r dr square, right, minus r cube. So cancelling out this term and this term, we are left with 4 by 3 pi dr cube plus 3 r square dr plus 3 r dr square, right? But dr is very small than r, hence dr cube very small than r cube, right? Hence neglecting this, hence neglecting term dr cube. Similarly, dr square is very less than r square, hence neglecting term with dr square dr square, right? Hence what we get is this is going to be dv. So we are going to neglect this term, right? And also this term. So what we end up with, this is nothing but 4 by 3 pi into 3 r square dr, right? Hence dr is going to be 4 pi r square dr, right? And this is what we are going to include in this expression, right? And when we do it, what we get is, we get the probability is nothing but pi square dv, pi square into 4 pi r square dr, which is nothing but 4 pi r square dr into psi square, right? Right? This is very important expression, right? This gives the total probability of finding the electron at a particular distance r, and this is also called as radial probability. Right? The plots of probability as a function of distance from the nucleus are called as radial probability distribution function, right? Or RDF. Let us write this down. So this gives the total probability of finding the electron at a particular distance r, right? This is called as radial probability, right? And the plots of probability, which is nothing but 4 pi r square into psi as a function of distance from the nucleus, which is nothing but r, is called as radial probability distribution function, right? It is clear that the radial probability distribution function graphs depend not only on the probability density but also on the volume of the shell. The probability density, that is the psi square for 1s, is maximum at the nucleus and it goes on decreasing with distance, right? However, the volume of the shell goes on increasing with increasing distance, right? The product of probability density and the volume of the shell gives the radial probability distribution function, right? So we can understand this from these plots, right? So this is the plot. Okay. Let us assume this is what psi square versus distance is r, right? And this is what is psi square. So this plot is of psi square, right? Psi square, right? And if we plot on the same graph, so this is going to be the volume, right? This is the volume of the shell, right? What is this going to be? This is going to be distance in r, and this is going to be probability, right? Probability, which is nothing but 4 pi r square into psi square, right? So this is going to be like this. This we are drawing for radial probability function for 1s orbital, right? So from this what we can see is that the probability density psi square of 1s is maximum near the surface, right? Is maximum near the nucleus and it goes on decreasing with distance. However, the volume of the shell goes on increasing, right? With increasing distance. The product of probability distribution, right? Probability density and the volume of the shell gives the radial probability. This is the radial probability and its product against the distance. So it reaches maximum and decreases, right? So this graph for 1s orbital shows that the probability of finding the electron is 0 at the nucleus and it keeps on increasing and becomes maximum at a particular distance from the nucleus, right? The peak of the curve gives the distance from the nucleus where the probability of finding the electron is maximum, and this is called as radius of maximum probability, right? For hydrogen atom, this distance is found out to be 0.529 angstrom, and this value agrees well with the value calculated by Bohr, right? However, it is important to note that the Bohr predicted that the electron will always be at R equal to 0.529 angstrom for hydrogen atom. However, according to wave mechanics, the probability is most likely to be found at this distance, but there is a probability of finding the electron at a distance shorter and larger than this value, right? So we should write this down. So from above graphs, from above graph. What conclusion we can draw is the graph shows that the probability of finding the electron is 0 at nucleus, right? It keeps on increasing and becomes maximum at a particular distance from the nucleus, and then gradually decreases, right? The peak of the curve gives the probability of finding the electron, right? Distance from the nucleus, where probability of finding the electron is maximum, right? And this is called as radius of maximum probability. Right? For hydrogen, this distance has been found out to be 0.529 angstrom, right? And this value agrees well with the value calculated by Bohr for the radius of first orbit, right? However, it is important to note that Bohr predicted that the electron will always be at r is equals to 0.429 angstrom, right? For hydrogen atom, right? However, according to wave mechanics, the electron is most likely to be found at this distance, but there is probability of finding the electron at distances shorter or larger than 0.429 angstrom, right? So this is very important. So now we are going to plot the probability distribution functions, or we at plots of probability distribution function versus r for various orbitals, right? So this is nothing but 4 pi r square psi square r, right? 4 pi r square psi square r, 4 pi r square psi square r, where this is the distance. This is what? This is our figure A, this is our figure B. This is figure C, and the whole figure is called as radial probability functions as a function of distance r from the nucleus, right? And this is for 1s orbital, this is 2s orbital, and this is 2p orbital, right? Right. So next what we are going to study about is boundary surface diagram, right? Let me drag a picture. The shapes of the orbital may be represented in terms of boundary surface diagram, right? So in this representation, so we'll do it afterwards. So in this representation, a boundary surface or contour surface is drawn for an orbital on which the value of probability density is constant. In principle, many such boundary surfaces may be possible. However, for a given orbital, only that boundary surface diagram of constant probability is taken to be good representation of the shape of the orbital, which encloses maximum probability density, right? So what is that we are going to try, right? The shapes of orbitals may be represented in terms of boundary surface plots, right? So this is the boundary surface diagram of 1s orbital, right? So s orbitals are non-dimensional and symmetrically spherical. This means that the probability of finding the electron is same in all direction at a particular distance from the nucleus. So this is the representation of 1s orbital, right? 1s, this is 2s orbital, and these are the directions, the coordinate axis, right? It is observed that the density of charged cloud is maximum at the nucleus and decreases with increase in distance from the nucleus, right? This is the region of zero probability, which is also called as nodes, right? So 2s, so 2s orbital is also non-directional, right? And spherically symmetrical. In this case, the probability density is maximum at the nucleus and becomes small at larger distance. However, the effective volume or size of 2s orbital is larger than 1s orbital. An important feature of 2s orbital is that there is a spherical shell within 2s orbital, right? This spherical shell, where the probability of finding the electron is practically zero, right? This is called as a node or nodal surface, right? This is called as a node. Thus, a 2s orbital differs from 1s orbital in being larger in size and having a nodal surface, right? So now we are going to study about the shape of, so we are going to add on the next figure, which is the 2p orbital, right? P orbitals. So these are the 2p orbitals. No, this is not the page, right? So we are going to find the image, right? So this is the figure, right? So this is the 2px orbital, 2py orbital, and 2pz orbital, right? So as you guessed, right, x stands for the direction in which orbital is presented. It is of dumbbell shape, right? This is y-axis, hence y. This is z-axis, hence z. For p orbitals, right, there are three possible orientations corresponding to ml equal to, so three possible orientation for p orbitals, for each for ml equal to -1, 0, and 1, right? This means that these are the three orbitals and three positions, right? So this is what we are calling px, this is py, and this is pz, right? And this representation is this, its representation is this, and its representation is this, right? So these three orbitals are equal in energy but differ in their orientation. Each orbital consists of two lobes symmetrically spaced about a particular axis. Depending upon the orientation of lobes, these are designated as 2p or 2px, 2py, 2pz, right? So this is 2px, 2py, 2pz. Accordingly, as they are symmetrical about x, y, and z axis represented respectively. 2px or that is 2px orbital has two lobes symmetrically spaced around x-axis, 2py around y-axis, and 2pz around z-axis. The shape of the orbital is called as dumbbell. Right? Shape is called as dumbbell, right? Right. So now we'll go study about the nodal surface, right? For this also we are going to drag a figure. Okay. So it may be noted that two lobes of the p orbital are symmetrically placed around a plane having zero electron density, and this is called as nodal plane, right? So this right here is a nodal plane for 2px, this is 2py, a nodal plane for 2py, and this is nodal plane for 2pz, right? So it should be noted that the probability of finding the electron in a particular p orbital is equal to both the lobes, right? The p orbital of higher energy values have similar shapes, although their sizes are bigger, right? So 4p is going to have larger size than 3p, which is going to have larger size than 2p, right? So now we are going to go on to the next topic, right? Which is the shape of the d orbitals, right? So these are the shapes of d orbitals, right? This is dxy, this is dyz, this is dzx, this is dx square minus pi square, and dz square, right? For d orbitals, L is equal to 2, right? For d orbitals, L equal to 2, that means minus 2, minus 1, 0, ml values 1 and 2, right? So there has to be 5 orbitals, right? So this corresponds to 2, minus 2, minus 1, 0, 1, and 2, right? And these are the boundary surface diagram, right, of 3D orbitals, right? So now we'll move on to the next topic, right? It is the energy level diagram for electrons, right? For this also we are going to drag a figure, right? Right. So the relative energies of various orbitals can be shown by arrangement known as energy level diagram, right? So let me write this down. The relative energies of various orbitals can be shown by an arrangement known as energy level diagram, right? It is clear from the figure that the energies of various orbitals in hydrogen atom depends only upon the value of the principal quantum number and independent of value of n, right? In other words, all subshells of given in the principal shell have the same energies, right? This is one. Given principal shell have same energies, right? So the order would be 1s less than 2s, which is equal to 2p, 3s equal to 3p, 4s equal to 4p, 4d, 4f, right? So on and so forth, right? Although the shapes of 2s and 2p orbitals are different, an electron has same energy when it is in 2s orbital or when it is in 2p orbital. The orbitals have the same energy are called as degenerate orbitals, right? And the electron in 1s orbital is called as is in the most stable state and is called as ground state electron, right? So what we are going to study about now is we are going to study about the of Bau's principle, right? What does this principle tell us that? Above principle. So what does this principle tell us that? It says that in the ground state of an atom, an electron enters the orbital of lowest energy first, and the subsequent electrons are fed in order in the order of this principle states that in the ground state of an atom, an electron enters the orbital of lowest energy first, and subsequent electrons are fed in the order of increasing energies. The word above in the German means building up, right? Right. So according to above principle, the orbital should be filled in above sequence, right? So the sequence in which it should be filled is 2s, then 2p, 1s, then 2s, then 2p, 3s, 3p, 4s, 3d, 4p, 5s, then 4d, then 5p, 6s, 4f, 5d, 6p, and 7s, right? It is very important to remember that the sequence of energy levels pertains to 3p and then 4s orbital, right? Right. So in order to explain this, right, so what we can do is we can drag a picture, right? So this is the way the electrons are going to. So you can remember it like this. So first 1s you can write like this is 1s, then 2, then 3, 4, all the orbitals in first orbit, second orbit, third orbit, fourth orbit, so on and so forth, right? And then you draw an arrow like this. So first it is going to be 1s. Then it is going to be the 2s orbital which is going to get this. Then it's going to be 2p and then 3s, right? Then it's going to be 3p and then 4s. After 3p it's not 3d, it's 4s, right? Then 3d, 4p, 4, 5s. Like this you have to continue. So this is the schematic diagram to remember the sequence of filling atomic orbitals, right? So the next is Hund's rule of maximum multiplicity, right? So what does this rule tells us that? According to this rule, electron pairing will not take place in the orbitals of same energy until each orbital is singly filled, right? Electron pairing will not take place in orbitals of same energy, that is nothing but same subshell, until each orbital is singly filled. So this suggests that it is difficult for an electron to enter an orbital which already has an electron than to enter an unoccupied orbital of the same energy, right? So this suggests that it is difficult for an electron to enter an orbital which already has an electron than to enter an unoccupied orbital of same energy. Unoccupied orbital. This is to be expected because there would be some repulsion between the electrons since their charge is same. Right? So this principle is very important in guiding the filling of p, d, and f orbitals, right? Which have more than one kind of an orbitals, right? Right? So last one, the topic which we are going to cover is the Pauli's exclusion principle, right? So as per Pauli's exclusion principle, what we have is, right? The last topic which we are going to study is Pauli's exclusion principle. Pauli's exclusion principle, what does it state? It states that this principle states that orbital can accommodate a maximum of 2 electrons and these must have opposite spins. Orbitals can accommodate maximum 2 electrons and they must be, they must have, and so this is related to the spin quantum number, wherein in spin quantum number, right, we have ms equal to plus 1 by 2 or minus 1 by 2. So this principle only states that this principle thus limits the accommodation of electron in an orbital. This means that an orbit can have 0, 1 or 2 electrons. Moreover, if an orbit has 2 electrons, they must be of opposite sign, right? So this principle thus limits the accommodation of electrons in an orbital, right? This means that an orbital can have 0, 1, 2 electrons. Moreover, if an orbital has 2 electrons, so in this class, what we have seen about the we have seen about radial wave function. Then we have also studied the plots of radial wave function for different orbitals. Further, we studied about the probability distribution, probability density graph, that is chi-square graph, for different orbitals. Then we also derived an expression for a radial probability function, and we plotted the radial probability distribution function as a distance apart. Then we also studied about the shapes of different orbitals, like s orbital, p orbital, and d orbital, right? We also studied about nodes. So nodes are basically regions of space where probability of finding an electron is 0. Then we also studied about the energy level diagram for an electron, right? Then we also studied about the electronic configuration of an atom, wherein we saw that we saw about this figure, right? So this is the order in which electrons get filled. Then at the end, we studied about 3 principles, which are the Pauli's exclusion principle, Afubow principle, and Hund's rule of maximum multiplicity. And with this, we cover the whole syllabus for this chapter, atomic structure, right? So I hope you have learned something in this lecture and in this tutorial series, and I hope you have enjoyed also. And I hope to see you again in the next class. Thank you.